So we're going to look at Markov chains and stochastic matrices. So this is a linear algebra that can model real-world phenomena. So this is really similar to some stuff we did in chapter 1 from section 1.10. So you should recognize it with one small difference. All right, so we've got City Car One Day Rental Company. They have 2 locations, one on Main Street, one at the airport. And of the cars rented at the airport, 80% are returned to the airport. And of the cars rented on Main Street, 30% are returned to Main Street. And today, half the cars are at the airport. So this is very much like the migration matrix stuff that we did earlier in the semester. What's different about this is that the vector of like what's currently happening in this chapter is always a probability vector. Rather than having actual amounts, it has percentages in it. So I'm going to make the stochastic matrix. This is what we used to call a migration matrix. So my stochastic matrix is just a matrix that's made of probability vectors. So I'm going to label this, I've got from, where you rent from and where you return to. And I'm going to have airport and Main Street, airport and Main Street. And then we just fill in the probabilities. So the cars rented at the airport, 80% are returned to the airport. So from the airport to the airport, 80%. And that means that if you rent from the airport, 20% get returned to Main Street. So your columns of your stochastic matrix are always going to add to 1. They're all, which is the definition of a probability vector. And then of the cars rented on Main Street, 30% are returned to Main Street. So from Main Street to Main Street gets a 30%, which means that 70% get returned to the airport. And again, that column adds up to 1. So that's called your stochastic matrix. Today's state vector. So today it said that half the cars are at the airport. So my state vector is airport, Main Street, half in the airport, half at Main Street. Is this a probability vector? Yes, the entries add up to 1. So what percentage of cars will be at the airport tomorrow? You can just multiply your stochastic matrix times today's state matrix. So I have 0.8, 0.2, 0.7, 0.3 times 0.5, 0.5, and I get 0.75, 0.25, and again, this is airport, Main Street. So what percentage will be at the airport? 75%. Okay. And then for the day after tomorrow, you just multiply your stochastic matrix times today, the current state vector. So we just do this again using the new state vector we just got. .75, 0.25, and we get 0.775, 0.225, and again that's airport, Main Street, so we have 77.5% at the airport the day after tomorrow. Then you just keep doing this, right? 3 days from now, just do it again. Take this new state vector you got, multiply by the stochastic matrix. What was it? 0.8, 0.2, 0.7, 0.3 times the new 0.775, 0.225, and you get 0.7775 and 0.2225, 77.75% at the airport 3 days from now. And 4 days from now, we just do it again. I'm not doing this to be tedious. Hopefully we're going to see a pattern here. 0.8, 0.2, 0.7, 0.3 times 0.7775. And yet 0.77775. So 77.775% at the airport 4 days from now. Okay, so what do you kind of see as a pattern? What's happening each time we do this? More 2s and 7s, yeah. So if we're just thinking about what happens at the airport, each time we progress a day, we're getting another 7 in there. So what do you think the limiting value is? If we did this like many times, what percentage is the cars at the airport approaching? 0.7 repeating, yeah. Each time we add a 7, right? So in the long run, my limiting value, actually, let me write it. The cars at the airport are approaching 77.7 repeating percent, which, yeah, would round to 77.8, but this is the limiting value. And 77.8 isn't a bad guess either. When you do like this, you are actually sort of, we've only looked at 4 examples and we take a guess at the limiting value. But if I want to actually solve for the limiting value, which we call the steady state vector, we have to solve a matrix equation. We want to solve P, Q equals Q. P is your stochastic matrix, and Q is the steady state vector that we're looking for. So we want to say, like, what would the values at the airport and Main Street have to be so that when you multiply by the stochastic matrix, nothing changes, right? That would be the limiting value. So that's what I want to solve. So to solve this matrix equation, I'm going to subtract Q from both sides so that I have P, Q minus Q equals 0. Because I want to use the tools of linear algebra where I would augment the right-hand side with constants. Right now I have variables on the right-hand side, so I'm moving everything over. And then I'm going to factor out this Q so that I have P minus the identity times Q on the right gives me 0 vector. So that's the matrix I want to solve. P is my stochastic matrix, I is the identity, Q is what I'm solving for, the steady state vector, or the long run behavior, in this case of the cars where they end up. Okay, so P was 0.8, 0.2, 0.7, 0.3. Minus the identity matrix, which is 1, 0, 0, 1, all of that, times Q, which is Q1, Q2, right? Percent at the airport, percent at the Main Street location, equals the 0 vector 0, 0. So that's the equation we need to solve. So 0.8 minus 1 is negative 0.2. 0.7 minus 0 is 0.7, 0.2 minus 0 is 0.2, 0.3 minus 1 is negative 0.7. Times Q1, Q2 equals 0, 0. And we would solve this just by setting up an augmented matrix and row reducing. And you get, so I'm going to write it down. One, negative 3.5, 1, 1, augmented, oops, 0, 0, sorry. Okay. So I have a free variable here, right? Which means there are infinite solutions to what I just wrote down. But I'm looking for one specific solution, right? I want to know the long run behavior, what percentage of cars are at the airport, what percentage are at Main Street. So if I write down what this says that Q1 is always 3.5 times Q2, and Q2 is free. But because I'm looking for a probability vector, Q1, Q2, I have one other restriction in that Q1 and Q2 have to add up to 1. Right? So somebody give me any solution Q1 and Q2. Sure. If I wanted to avoid having decimals, I could say 2 and 7, right? You said 1 and 3.5, that's a solution. 2 and 7 is a solution. But this is not a probability vector, right? So I need to actually find a solution that satisfies this, but adds up to 1 also. So a quick way of doing it is if you just add your two, pick any solution, like we just came up with one, add them together, what do you get 9, right? And then make those your denominators. So you end up with 7/9 and 2/9. So that should work, right? If you choose Q2 to be 2/9, 3.5 times 2/9 gives you 7/9. So the answer to the question, right, is that the number of cars at the airport approaches 7/9, which is 77.7 repeating percent. Have any questions? So I picked any solution Q1, Q2, right? Yanni had suggested 1, 3.5. And I was like, I don't really like decimals, so I'm going to pick 2, 7. You can pick any solution you want, right? And then my restriction on Q1 and Q2 is that it has to be a probability vector because I'm looking for the percent at the airport and the percent at Main Street. So I need these two entries to add up to 1. Add the two entries together. 2 and 7 gives you 9, or 3.5 and 1 gives you 4.5, right? So you could do 7/9 and 2/9. You just add the two entries together and make it the denominator. You could do the same thing with the 1 and the 3.5, right? I could do 3.5 over 4.5 and 1 over 4.5. But then I'd be like, I don't like decimals in my fractions, so then I would probably get rid of them. But that still works.